discussing a time reversal symmetry and how it restrains the form of a general block Hamiltonian. And what we found last time, this is just a recount of where we stopped, is that for a time reversal invariant Hamiltonian, we have a condition in the case, again, of spinless fermions that a complex conjugate of the block Hamiltonian is equal to that Hamiltonian at minus momentum k. And then from this, we derive that if an eigenstate u exists at energy epsilon k, then for a Hamiltonian with this property, an eigenstate u star at minus k is the eigenstate of the same Hamiltonian at this energy E minus k, which implies then, so in other words, u of k is an eigenstate of this Hamiltonian, and u star of minus k is an eigenstate of the same Hamiltonian, which implies that we can order our eigenstates in such a way that we identify uk star and u minus k, and it also implies that the energy is symmetric with respect to k equals 0. So this is an important property of a time reversal invariant Hamiltonian. And it's important for us because it implies vanishing sigma xy and the Chern number for T invariant systems. So this is a kind of important consequence of the time reversal invariance. And let's just show that this is the case. So one can write down the Berry curvature. Remember the Chern number here, n, is an integer, and it's given by the integral of the Berry curvature over the full Brillouin zone. And one can write for this Berry curvature Fij, and let me write the Berry curvature Fij at minus k for the reasons that will become clear. And according to the definition that we wrote down earlier, this Berry curvature can be written in components as follows. Partial derivative of I of u at minus k, inner product, partial derivative of j u at minus k, inner product, minus the same term with I and j interchanged. Right? So we had a kind of more compact notation, but if I, in the definition, if I write it in detail what that compact notation means, then it means this. And now what we can do, we can use this for time reversal invariant Hamiltonians. We can replace u minus k with u star k. Right? So let me do that. So I get minus I di u star k dj u star of k, and again minus the same term with I and j interchanged. But remember the properties of inner product. I can take this star out to the outside of the inner product because the derivatives themselves, they are real, so they don't really complex conjugate in any way. But then I can use the property that AB star is the same as BA, right? So basically, I just erase this star, put it up here, and then use this property which interchanges the two. And let's see what we get from here. So we get minus I dj uk di uk minus I minus j. But then I regard this expression and notice that basically this thing here, this inner product, is exactly equal to this one, or, well, the one with I and j exchanged. So this is nothing but minus Fij, but at k. Okay? In other words, what I find when I look at the beginning and the end is that in the case of time reversal symmetry, the Berry curvature is odd under the change from k to minus k. And this means that when I integrate it over the Brillouin zone, so the Chern number, remember, is the integral of 1 over 2 pi over the Brillouin zone d2k of fxy of k. So I can take, say, I have a square Brillouin zone, right? And I can divide that integral into integral over positive, over these momenta, k. But then the integral over the other half of the Brillouin zone will be exactly opposite to, because of this property, right? So just I'm integrating an odd function over a symmetric interval, and this will therefore vanish. So I can write this as 1 over 2 pi integral over 1/2 Brillouin zone minus the integral of that 1/2 Brillouin zone. And this just has to vanish for time reversal invariant system because of this antisymmetric property. So I come to an important conclusion that both sigma xy and the Chern number is necessarily 0 when I have a time reversal invariance. Okay, so the second symmetry that we're going to consider for graphene is the inversion symmetry. And let's do this quickly because we have already everything in our hands. So the inversion symmetry, often denoted as P, takes r vector into minus r, and similarly P to minus P. It doesn't do anything with time. This is spatial inversion, so time remains unchanged. And this one is a unitary symmetry. Because the operator acting on this commutator just gives me back RP, right? Because both of them are odd under inversion. Their commutator is even under inversion, so I don't need to do any complex conjugation. So in other words, there's no complex conjugation. And let's see how time reversal, how inversion acts in graphene. So let me draw the graphene hexagon here. And these are our A sites, and the rest are B sites. And I can identify 4 different centers of inversion in graphene. Clearly, the center of a hexagon would be a center of inversion because it maps this point onto that, this on that, and so on. But there is more, a center of each of these bonds is also a center of inversion. You can convince yourself of that. But in any case, the important point is that in graphene, P interchanges A and B sublattices. In other words, you cannot find an inversion center that would not do this. And therefore, in graphene, we identify inversion like this. The real space creation operator under inversion goes to sigma x times C minus R, where sigma x is 0, 1, 1, 0. So you can see that if I'm viewing this C of R as a two-component spinner in the sublattice space, and this acting with the sigma x just interchanges the two sublattices. Or similarly, in momentum space, C of k maps under inversion to C of minus k. And again, the fact that R and minus R, that R maps onto minus R is that basic property, and similarly with momentum. Okay, so for the Hamiltonian, similarly as we derive this property for the Bloch Hamiltonian by simply considering that property of the time reversal operation for inversion symmetry, we could similarly go over the motions, and we would find that the property that Bloch Hamiltonian needs to satisfy in order to be inversion symmetric is this. So there is, again, no complex conjugation involved, but there is a conjugation with this sigma x matrix, which interchanges A and B sublattices, and that symmetry must be satisfied if we are to call Hamiltonian inversion symmetric. Any questions about this? So let's now finally put this to some use, and let's see how in graphene the combined time reversal and inversion symmetries constrain the form of the Hamiltonian. Okay? So the Bloch Hamiltonian in graphene we wrote in the following form. And this is before we linearized near the Dirac point. We wrote it like this. And now let's ask the question, under combination, of T and P, what happens? Okay, we want the Hamiltonian to be invariant under both time reversal and inversion symmetry, so let's combine them. In other words, we're combining this property with this one, right? And you can see why I want to do that. Both time reversal and inversion symmetry relate Hamiltonian at momentum k to momentum minus k. However, when I apply both of them, I will get a constraint for the Hamiltonian at the same k, right? So combined action of T and P can be expressed like this. Sigma x h of k, sigma x is h of k. Right? So I'm first you can think of it this way. I'm first applying the inversion symmetry. So I'm using this equation. And then I'm replacing h minus k with h k star. And then I'm starring the whole equation. And since these are real matrices, this is what I get. Okay, so this is a constraint for my Hamiltonian at the same momentum k. And this actually tells me something about the allowed terms in this Hamiltonian. So let's look at the three terms in turn. This can be written as d1 sigma x plus d2 sigma y plus d3 sigma z, like so. And let's see which of these terms are allowed under this condition. So let's look at the first one. First of all, we know that these d's have to be real, otherwise the Hamiltonian would not be Hermitian. So I take a complex conjugate of this, but sigma x is real, so that doesn't do anything. Then I conjugate it with sigma x, and that doesn't do anything either, right? Because sigma x commutes with itself. So that tells me that d1 is unconstrained, right? Nothing, I get no constraint about d1. Let's look at the d2 term. First of all, I complex conjugate it. This is imaginary, right? So I get a minus sign. But then I conjugate it with sigma x. That minus sign disappears because sigma x and sigma y anti-commute. So I end up with no constraint on d2. However, d3, when I complex conjugate, nothing happens. But when I conjugate with sigma x, it anti-commutes with sigma z. So I get a condition that d3 of k has to be equal to minus d3 of k, which tells me that d3 has to be 0. So the constraint that I get from the combination of time reversal and inversion is that d3 term is excluded. And that's the same as to say that the Hamiltonian has to remain massless or gapless when these guys, when only d1 and d2 are present. Yes?
And d1 and d2 are real valued functions.
Yeah, real valued functions of k, just because otherwise the Hamiltonian would not be Hermitian. So the conclusion here is that as long as T and P are maintained, d3k is 0, and graphene remains gapless at k equals plus minus capital K. Now, why is this? Well, this is simply because we showed that d1 is proportional to q, which is a small deviation of k from k, and similarly qx in this case, and d2 was proportional to qy, right? And if you so you can say, well, but perhaps I can add under these symmetries. It is allowed that I add some small constant to this qx, but that of course would not gap out the Hamiltonian. That would just shift the point where this d1 vanishes, right? So you could actually, under those, while maintaining those symmetries, you could move around those point nodes, but you cannot gap them out. Only adding a term in d3 that would correspond to a mass term for a Dirac Hamiltonian. Yes?
This is like saying if you were to distort your lattice slightly, then you get like a shift to the k points
Exactly, yeah. So you can conceive of distortions of the lattice where these point nodes would shift away from these high symmetry points, but they would not disappear. Let me just note, and I will not elaborate on that, is that the C3 rotation symmetry further restricts Dirac points to be exactly at plus minus k. So if you add to these time reversal and inversion symmetry the fact that the lattice is invariant, undistorted lattice is invariant under a 120-degree rotation around certain points, then you can show that those gapless points have to remain at the corners of the Brillouin zone. But this is really not going to be important for our further consideration, so I will not elaborate on that. Yes, question?
I remember seeing a result that if you strained graphene, like a graphene sheet enough, you could force two K points to shift on top of each other, in which case they would break.
Yeah, okay. So that's a good point. So what Tom is saying is that if you deform the lattice while maintaining time reversal and inversion, so that these Dirac points shift significantly, they can actually annihilate one another. So when two Dirac points come together, then they can actually disappear. But that would not be a small perturbation. That would be really a large perturbation. So we're not really, again, this is not something that is important for us here. Okay. So one more thing that I would like to say about the symmetries. So how do these symmetries act on the low energy theory? So the only important point here is that, remember, we expanded the Hamiltonian around k like this, k plus q in valley 1, and then we expanded k around minus k plus q near valley 2. Under both time reversal and inversion, k goes to minus k, which means that the two valleys are exchanged under both time reversal and inversion. So what that means is that in the low energy theory, we have to implement that. And it follows then that time reversal invariance for the low energy Hamiltonian is implemented like this. And the inversion looks like this. Okay, so this is exactly the same expressions as we had before for the full Hamiltonian, except that I'm adding this tau x, which interchanges the two valleys, consistent with the fact that the full momentum goes to minus itself, not just this deviation from the Dirac point. So this is the action of the two symmetries on the low energy effective Hamiltonian. Okay, so let's now discuss, now that we know what the symmetries of undistorted graphene are, let's now discuss ways of breaking those symmetries. And this goes under the name of mass terms. And once again, the reason why I'm talking about mass terms, I'm making an analogy with high energy theory. The low energy spectrum of graphene is massless in analogy with a massless Dirac fermion. And what I'm interested in is finding perturbations that will open up a mass gap here. So this would be massive. And again, we showed that as long as these symmetries are maintained, this is not possible. So we're looking for perturbations to the Hamiltonian that break either one of those symmetries. And there's two mass terms that are discussed in the literature. So let's discuss them in turn. The first one is the so-called Semenoff mass. And this has been first discussed by Gordon Semenoff, who's a faculty at UBC. He's actually a string theorist, but nevertheless, he did this work in graphene. And he's still quite interested in graphene, actually. And so what he proposed was adding a term to this low energy theory that looks like this. Delta H, and I put index S here for Semenoff, is simply sigma z times ms. So basically, this is something that is not allowed by these symmetries, because we said that anything proportional to sigma z is disallowed by the combination of the two symmetries. So let's see which of the symmetries are broken. Under time reversal, we have tau x delta h s star. Tau x, this is momentum independent, right? It's real. We're taking real mass for it to be Hermitian. And we see that basically this goes back onto hs, because tau x commutes with sigma z. They act in different spaces. It's real. So under this perturbation, the time reversal is not broken. It's fine. Let's check the inversion symmetry. In this case, we have to conjugate this with sigma x, and again, sigma x, tau x. And now we see that, again, tau x doesn't do anything as before, but sigma x anti-commutes with sigma z. So we conclude that this is equal to minus hs. This term indeed is odd under inversion. So inversion symmetry is broken, and we conclude that the Semenoff mass breaks the inversion symmetry. And therefore, nothing stands in the way of opening such a mass gap. So let's check explicitly. So let's write the full effective Hamiltonian. And this looks like this. Vf tau z sigma x qx plus sigma y qy plus sigma z times ms. And if you just look at this Hamiltonian, you notice that all three terms anti-commute with one another. We already know that these two terms anti-commute with one another. but the third one anti-commutes separately with this one and that one. So the spectrum will simply be the square root of the three terms added up. And I can check that explicitly as we did before. I can square HF. And what I get is simply VF QX squared plus QY squared plus MS squared, right? The fact that each term anti-commutes with each other term means that I will have no mixed terms. I just have all these terms squared. And if you don't see it right away, I invite you to check and use all the commutation algebra to convince yourself that this is the case. And from this, one finds E of Q simply be plus minus square root of VF squared Q squared plus MS squared. And clearly, this is a gapped spectrum because when Q goes to 0, this goes to plus minus MS, which is a constant. So this indeed, at low energy, would look like this with a spectral gap of 2 ms. So what does this correspond to physically? The physical realization is a staggered on-site potential namely, when I take this, again, this hexagon, and then I impose plus ms on A sites and minus ms on B sites, then this is clearly the perturbation that gives me this type of a mass term. And this is simply because, remember, this sigma z is just a matrix with plus 1 and minus 1 on the diagonal, and the sigma z acts in this AB sublattice space. So this is precisely the perturbation that one gets. And in real life, this type of perturbation, actually, people know how to engineer. And this is realized by growing graphene on boron nitride sometimes abbreviated as BN substrate. And boron nitride is a layered crystal, and in each single layer, it has the same honeycomb structure like graphene, but instead of carbon atoms occupying each of the crystalline positions, you have alternate structure of boron and nitrogen. So you have two distinct atoms. Let me just draw that for you explicitly. So boron nitride looks like this. And these guys are borons, not morons, but borons. And these guys are nitrogens. And so clearly, since these are different atoms, when you put graphene on top of this, these various sites should feel different on-site potential because they are inequivalent in this structure. And this has been seen experimentally that indeed when you grow graphene on boron nitride, its spectrum looks gapped rather than gapless. Any questions about this? Okay, so this is not the end of the story. And also, this by itself is interesting, but maybe not so super interesting because we showed that this mass term breaks inversion, but no time reversal. And since time reversal is unbroken, this will be a topologically trivial phase. We showed that the Chern number necessarily has to vanish in this case, right? So is there some other mass term that would break time reversal and could lead to potentially topologically non-trivial phase? And the answer to this is yes. And this goes under the name of Haldane mass. And this has been published in PRL 61.215.1988. And Haldane mass looks like this. Delta H Haldane is tau z sigma z mh. So it looks a little bit like Semenoff mass, but it also has opposite sign in the two different values. And you can check by the same analogy that under T, this transforms as odd. So time reversal is broken, but under inversion, it transforms as even. So inversion symmetry is maintained. Once again, the spectrum would be exactly like this with MS replaced by MH, and one can show that very in an analogous way. And lattice realization is slightly more complicated. It's imaginary valued second neighbor hopping. In other words, once again, let me draw the basic hexagon. And to realize this type of Haldane mass, what you have to add to this is second nearest neighbor hoppings that are imaginary valued. So I times lambda, I times lambda, I times lambda, like so. And the same thing for the other pair of second nearest neighbor hoppings. And I have to assign these arrows because I have to, when it's imaginary, I have to say in which direction I take plus I lambda, because in the opposite direction I have to take minus I lambda, so that the Hamiltonian remains Hermitian. And I will not show this explicitly, but again, you can just go back to the tight binding model, put down these extra terms, expand everything near the nodal points, and you will find that it leads to this type of term in the low energy approximation. And specifically what you will find if you take these lambda to have strength lambda, then you would find that this Haldane mass would be 3 times square root of 3 lambda h. And the square roots of 3 comes from the distances that in this lattice are always some square roots of something. Yes, question?
What's the relationship between this and the torque?
This and what?
Torque? And so on, or am I just making?
I don't think there is a direct relationship. Okay. So let me do one last thing. And let me explicitly calculate now the Chern number for the case of Haldane mass. And according to this, now time reversal symmetry is broken. So this conclusion that we reached there does not prevent from a Chern number to be non-zero, but it doesn't mean that it necessarily is non-zero. It turns out to be non-zero, but let's just quickly show that. So the Chern number and the Chern number, like I already said, is calculated like this. Where Fij is written like this. Or this is the convenient form for calculating this Berry curvature. And one can actually show, and I will not do that, it's about 2 lines of simple algebra, that this can be rewritten, and this is going to be slightly more useful for us as follows. This can be written as 1 over d cubed times d dotted into di d cross di d. So instead of working with unit vectors, we work with full vectors, but then we have to divide out the magnitude cubed. And this can be shown mathematically that it's true, but physically what this counts is the total volume angle swept by this unit vector d. But of course, if you make that unit vector longer or shorter, doesn't really affect that angle. So this is also true. Okay. So there's a number of ways to calculate this. Now, what one would like to do, but that's kind of technically a bit difficult, one would like to put the full lattice Hamiltonian into this formula and then calculate what this is and perform that integral over the Brillouin zone. Now, you can just imagine in your mind that that's going to be a bit difficult because that lattice Hamiltonian contains all those sines and cosines, and just finding this and then d cubed in the denominator, that's going to be a mess. It can be done, but I don't want to inflict that pain on anybody. A much simpler calculation follows from simply calculating this in the low energy approximation, where we will see that actually all the contribution almost to this integral comes from the vicinity of those corners of the Brillouin zone, namely from the vicinity of these points. Okay, and that calculation is actually simple. So let me do that calculation, because we can do that in a few lines rather than in 2 full blackboards. So once again, in the low energy calculation, so we do calculation for a single Dirac point, and then we add up the 2 Dirac points. So near a single Dirac point, again, our H effective of Q has this form d of Q dotted into sigma. And the nice thing about d of Q is that it's simple, right? It has the form Vx, Qx, Vy, Qy, and some m. Okay? And I'm keeping these guys general because they will be different for different Dirac points, right? Where is my Hamiltonian? Here, it's Vf, but it can be plus or minus depending on which Dirac point are we near. And with this a simple d, I can actually very easily evaluate this expression. So for instance, the x derivative of d vector is, I'm taking a derivative with respect to qx. Qx only appears here, so it's just this, Vx 0, 0, right? Dy derivative of d. Similarly, qy is only here, so it's 0, vy 0, and dz derivative of d is just a 0 because there's no dependence on qz. So now I can calculate this piece here, right? So what I'm calculating is the whole fxy will be 1 over 2 d cubed, and I will add d cubed. Later, now I want to calculate this inner product with cross product of the two things, and this is going to be a determinant of d. So let me write d in its components: vx, qx, vy, qy, m. And then I have to dot it into x derivative, which is this. So I write vx 0, 0. Here I write the other one, right? And this determinant is easily evaluated. The only non-zero term comes from taking this m and this subdeterminant. So this is going to be equal to 1 over 2 d cubed vx vy times m. Okay? So now I have to plug this in to this formula. Well, first, just plug it in to that formula and perform that integral. So n is 1 over 2 pi integral dqx dqy vx vy m, and then in the denominator I have twice this d cubed, which is vx qx squared plus vy squared qy squared plus m squared to 3/2. And now I can scale things, and it's just a simple integral. So I can take out, well, okay, let me just do this. So I define new variables. X is vx times qx, whereas y is vy times qy. And what I get from here is sine of vx vy divided by 4 pi integral dx dy m divided by x squared plus y squared plus m squared over 3/2. And now, of course, I just have to integrate this over the Brillouin zone. But if I study the integral for small m, I can see that most of the contribution comes from the region of the Brillouin zone when both x and y are small. So what I do, I just extend the integration boundaries to infinity and hope for the best. And this can be done better, but when I do that, I find that this integral is equal to 1/2 sine of vx vy and m. Okay? And now this has the right flavor because this is supposed to be a topological invariant, right? So it better not depend on any details. And indeed, I'm finding that it depends only on the sign of my some of my input parameters. Otherwise, it's basically, this is basically plus or minus 1/2 depending on sign of this product. Okay, and actually when you calculate these topological invariants, they always come out like this. They always come out as a sign of something, because if something is to be an integer and you have a theory with all sorts of continuous parameters, that's the only way that things can actually work out. Okay, so we came to a conclusion that for a single Dirac point, I have a contribution to the Chern number that is plus a half or minus a half, depending on the sign. And from this, we can now see what it is for the Semenoff mass and what it is for the Haldane mass. And basically, so let me just evaluate that. So for Semenoff, what we have is the following. We have a valley 1. We have a Vx is equal to Vy is equal to Vf, and M is equal to plus M Semenoff. For valley 2, we have minus Vx is equal to Vy is equal to Vf, and M is equal to minus Ms. And this simply comes because this sigma z here tells us that for one valley, this should be the same. What I was going to say, this minus sign simply corresponds to this tau z matrix, which tells me that these velocities are different for different valleys. And you can then see right away from this that I'm basically adding 1/2 sine of Vf squared times Ms plus 1/2 sine minus Vf squared times Ms, which is 0, right? And this is in agreement with our general proof that when you don't break time reversal symmetry, the Chern number must vanish. On the other hand, for the Haldane mass, one finds that for valley 1, again, Vx is Vy is Vf, and M is now equal to M Haldane. However, for valley 2, the velocities are the same. That didn't change. But here, M is equal to minus mh, just because for a Haldane mass, I have this tau z, which again tells me that the masses change between the two valleys. And so the calculation here is just basically one sign makes all the difference. I get sine Vf squared M Haldane plus 1/2 sine Vf squared M Haldane, which is just sine of M Haldane, which can be plus or minus 1. Okay? And I'm just taking advantage of the fact that the sine of Vf squared is always positive because it's a square, whereas mh can in principle be positive or negative. So the grand conclusion here is that Haldane insulator or let me write it like this. Graphene with a Haldane mass is a Chern insulator with sigma xy equals e squared over h times sine of Haldane mass, while with Semenoff mass is trivial in the sense that sigma xy is 0. So this is the conclusion of our discussion of graphene.
So
Yes.
if you break, I mean, currently, like, the masses you put on are invariant over, like, you know, you have translational symmetry.
Yes.
If you break that with the Haldane mass, do you get the same channel?
Are you thinking about some non-uniform Haldane mass that would fluctuate in space?
Yeah.
Well, that's a good question. And there's no simple answer. The answer is if you start from a uniform mass that is relatively large and you add to it small fluctuations so that they don't close the gap on average, it remains in this state. However, when the fluctuations become comparable to the size of the gap, then you break it up into domains which may have opposite Chern numbers, and then all sorts of things can happen.
And so then you get like a boundary.
Yeah. Yeah. So this is the last thing that I want to mention. So here's a kind of question that one may ask. So I have a gapped system here. When I focus on Haldane mass insulator, but nevertheless it exhibits non-zero Hall conductivity. So how do the electrons flow in an insulator, right? And the answer is provided by the edge concept of the edge state. And this is something that you will discuss in more detail today in the tutorial. What you can show, and you will show this explicitly, if you consider a boundary between Haldane gap and Semenoff gap, and let's say you have a Chern number equal 1 here, and here you have necessarily Chern number equal to 0, then what happens is that the two masses, one goes like this, so this is, say, M for valley 1, but the other one changes sign. It goes from negative to positive, so this is M2 as a function of some coordinate here. Let's this be x coordinate. So this is 0, right? And that's just here, right? So on one side, one is positive, one is negative. On the other side, both are positive. So if I just plot it, and at the boundary, there has to be one of them has to cross over through 0. And when this mass crosses through 0, then effectively along this boundary, the system is gapless. And there will always be a gapless edge state along this boundary. So this is the edge state, and there will be exactly one state that propagates. And it turns out that the sigma xy, the whole conduction, is actually produced by this edge state. So when you apply leads to this sample, right, instead of current flowing through this gapped bulk, it actually flows along the edges, and that's what you measure. But these edges, again, just like in the case of our one-dimensional case, are determined by the bulk. There's this bulk boundary correspondence. The fact that you have a difference between Chern numbers between the two sides of your system necessitates the existence of this edge state, and it is that edge state that actually gives you this quantized, precisely quantized sigma xy. Now, I gave an example of a boundary between Haldane gap and the Semenoff gap, but even if you take any other system which has 0 Chern number, like vacuum, for instance, that edge state cannot be removed. That is there simply because it's protected by the existence of the bulk Chern number. Yes?
If I went to the Semenoff, if instead of having the Semenoff state there, I just have like the Haldane state, but with the masses flipped, I get the same channel minus 1.
So the general statement here is that number of edge states equals delta n, which is absolute value of n1 minus n2. So if I have two media with different Chern numbers, then the number of edge states between them is always given by this difference in the Chern number. So no matter how you arrange these systems, then that is always the case, and that then gives you the precisely quantized Hall conductance. Okay. If there's no more questions, this concludes our discussion of topological states. And for the rest of the, what do I have, 2.2 lectures that I still have, we will be discussing another amazing phenomenon, which is superconductivity. Superconductivity was discovered in 1911 by Kamerlingh-Onnes. Who, by being the first person to be able to liquefy helium, he studied all sorts of things, how things behave at those very low temperatures. For instance, before this monumental discovery, he was freezing little frogs and trying to see what happens to them at liquid helium temperatures, and nothing really much happened to little frogs. But then one day, what?
What is it with physicists and frogs?
Oh, yeah, I don't know. One day, he was actually at a conference reporting maybe about frogs or something, and his assistant, who was doing experiments on things, reported to him that when he cools mercury down to 4.2 degrees Kelvin, then suddenly the resistivity of it, electrical resistivity, drops to 0. And Kamerlingh-Onnes says, ha, 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 I mean, that's just some problem in your apparatus, so check everything and then report back. And so the assistant, whose name I forgot, unfortunately, checked dutifully everything and didn't find any problem, and this experiment was reproduced several times in their lab. And then Kamerlingh-Onnes got a Nobel Prize for this, and the assistant remains unknown. So that's how it goes. Now, I will, so superconductivity in this discovery is a zero resistance state. And perhaps even more fundamentally, it's a state of matter that exhibits Meissner effect. Which is expulsion of magnetic field from the interior. So basically, when you have a superconductor in the magnetic field, and well, initially it's at high temperature, you cool it down across its transition temperature, it will completely expel all the magnetic field from its bulk. And according to our modern understanding, it is this property that really is fundamental for a superconductor, because nothing else does that. In principle, if you had a piece of metal that is extremely clean, you're able to remove all the impurities, you clean it down, you cool it down so that phonons don't scatter, it would also be in principle in the state of zero resistance, but it would not expel magnetic field. That's a unique property of the superconductor. Now, I will assume that all of you have had some exposure to superconductivity in a sense that in an undergraduate course, typically, you would get some phenomenology So you would learn about zero resistance state, Meissner effect, and all the other phenomenology, like the existence of energy gap, the Josephson effect, the flux quantization, and so on. If you've never heard about those things, I will not review them here, but I recommend that you read Ashcroft and Mermin, chapter 34, where these are beautifully discussed. And there's lots of interesting phenomena associated with superconductors. What I will focus on is microscopic theory, and specifically the BCS theory of superconductivity due to Bardeen, Cooper, and Schrieffer. And this is 1956. So this is a remarkable piece of physics. It took 45 years from the discovery of superconductivity to the formulation of the correct theory. 45 years, half a century. And that's just because at the turn of the century, we simply didn't have the machinery, or people didn't have the machinery to understand superconductivity microscopically. People had to develop, basically the whole quantum mechanics, and then the many-body theory, condensed matter physics, and so on, in order to do this. And then still it took these leaps of imagination by basically these two guys. So Leon Cooper was a graduate student when he came with his big idea of a Cooper pair, and we will discuss that next. Bob Schrieffer was a postdoc in the group, and he came with the famous BCS wave function, apparently as he was riding a subway in New York City, the story goes. And Bardeen, who was then a senior professor, he already had a Nobel Prize for invention of transistor with Brattain and Shockley back in the 40s. He kind of coordinated the effort and inspired these young people, and then put things together once these ideas were formulated. But it's a kind of amazing piece of theory that explained this. We just celebrated 100 years of discovery of superconductivity 3 years ago. And what you can find online is this compendium of famous physicists who tried to develop theory of superconductivity before BCS. And this included Albert Einstein, Feynman, Fermi, and all these luminaries. And they were all wrong. So it's a kind of satisfying reading that you read a paper by Albert Einstein, and it's just completely off the track. He's trying to explain superconductivity through some weird mechanism, and now we know that they were just completely off. So if you're kind of interested in some history, then you can download this for free and look at how all these luminaries went wrong. But these guys then got the idea right. So we have about 20 minutes. So let me start discussing the first key point in BCS theory of superconductivity, which is the so-called Cooper instability. So our goal here is to explain these phenomenological facts that superconductors expel magnetic field, and they have a zero electrical resistance. So we're going to build a theory, and at the beginning, it will maybe not be clear at all why this is what's happening, but in the end, hopefully, we'll tie everything up and explain this important phenomenology. So this is 1956, Leon Cooper. And what he showed is the following remarkable fact. He showed that for an arbitrarily weak attractive interaction, electrons in the Fermi sea are unstable towards formation of pairs. Today we call them Cooper pairs, but technically they are electron-electron bound states. So the problem he considered, now also known as the Cooper problem, looks like this. Imagine you have a Fermi sea. So all these electron states in the Fermi sphere are filled. We consider T equals 0. One can extend this theory to non-zero temperatures, but let's start at T equals 0. And now what he considered were two electrons just above the Fermi surface at two opposite momenta, and I will comment on that in a moment. So there's an electron right above the Fermi surface at momentum k, and another one at momentum minus k. And he described them by the following simple two-body Hamiltonian, P1 squared over 2m plus P2 squared over 2m plus an interaction R1 minus R2, which he considered to be weakly attractive. And then he showed that under these conditions, the two electrons are unstable towards a formation of a bound state, whose energy, and this is the important thing, is actually lower than the energy of the just a free electron that you would put on the Fermi surface. And another important thing is that this only happens in the presence of the Fermi surface. If you just take two electrons in free space with the Hamiltonian like this, then this would not happen. You would need strong attractive interaction to form a bound state in the presence of a Fermi surface. However, the kind of key insight was that this happens for arbitrarily weak attractive interaction. Okay, so let's go through this solution, which is relatively simple. We follow Cooper and make two assumptions, reasonable assumptions. First, we assume that electrons have total momentum 1 and 2. Our two electrons have total momentum 0. In other words, their respective momenta k and minus k are opposite. And second, we assume that they are in spin singlet state. So electrons, here we no longer can avoid spin. In discussion of graphene, we avoided spin. Here we won't be able to do that. Spin is essential for this Cooper problem. And so these are the two assumptions. And maybe I can move to the other blackboard so that people see better. So what this means symbolically is that the two-body wave function of these two electrons can be written like this. Okay, so let me explain. So first of all, I'm expanding the wave function in plane waves. I'm taking into account the fact that the two momenta, the total momentum is 0, so momentum of one is k, then the other one is minus k. G of k is some unknown function to be determined by solving that Hamiltonian. I'm including the Fermi sea by restricting this momentum summation only to states larger than kf, because these electrons, the Fermi sea is occupied by all the other electrons in the problem. And the fact that I'm in spin singlet state is symbolically written here. This is the spin wave function of the problem. And I can deduce, so the fact that this wave function is antisymmetric under the exchange of two electrons is taken care of by this spin factor. So the wave function under the exchange of the coordinates has to be now symmetric, because spins already do antisymmetry. If it was spin triplet state, then this part would be symmetric, and I would have to insist that this part, the orbital part, is antisymmetric. So in other words, Fermi statistics implies that G of k is equal to G of minus k. Again, just because I want the spatial part to be symmetric, because the antisymmetry is already in the spin part. Okay, so let's we do what we always do. We take this wave function, we plug it into a Schrödinger equation with that Hamiltonian. So we write H psi naught is equal to E psi naught. And then we do the usual thing. We multiply by these plane wave factors and integrate over the coordinates. And we end up with an equation for this G. And again, I will skip these steps because we did this already many times. And we end up with an equation for G, which is the unknown here, of the following form. Where epsilon k is just the usual free energy of my electrons, and Vk k prime is a Fourier transform of my potential. Okay, so this equation is just fully equivalent to this original Schrödinger equation, and Vk prime is the Fourier transform of that potential. Now, so Cooper, in his wisdom, didn't try to solve this equation for some extremely realistic potential, but he made a very simple ansatz for this potential, which makes this equation exactly soluble. And so following Cooper, we take the following ansatz for this Vk k prime. We simply say that is equal to minus V, where V is some positive constant, when epsilon k minus epsilon f and epsilon k prime minus epsilon f are both smaller than some cutoff that we call h bar omega c, and then we take it to 0 otherwise. So this is to say that whenever both of these electrons at k and k prime are within some some narrow band of the Fermi surface whose width here is h bar omega c, then they interact with this attractive interaction V. And when they are outside that band, then that interaction is 0. This is motivated by some calculations that we don't have time to go into, and by some experimental work that was known at the time and is even better known today. So although the actual interaction is almost certainly not step-like this, it has roughly this property that when these energies are much larger than some cutoff, it goes to 0, and when they are smaller than a cutoff, they go to a constant. So this is a kind of simple but realistic approximation. So we can substitute it in there and simplify the equation like this. E minus twice epsilon k acting on gk is minus v sum over k prime. And I put a prime on this summation, gk prime. And this prime now means that k prime is greater than kf, which was the original condition on the sum. And also, I need to insist that epsilon k prime minus ef is less than h bar omega c, which comes from this fact, because when it's larger, then that term is 0. OK, so what I can do now, I can solve this equation. I can express g of k by dividing through with this denominator here. And I can also switch the signs around. So I get k prime gk prime to epsilon k minus e. And then the way you can solve equations like these is the following. You can perform a sum now over k with the same prime on top. And you see that this thing here does not depend on k anymore. Right? That's how we selected our interaction. When I perform a sum over k on the left-hand side, then it's going to be the same sum as this one. They just differ by me using different dummy summation variable. So the sum over g of k just drops out, right? And I will end up with a simple equation that looks like this. 1 over v is equal to sum over k with the prime 1 over 2 epsilon k minus e. And let me put a box around this equation, because this we can now solve. This is just some equation where we know v, we know epsilon k, and we want to solve it for the energy, which will be the energy of our putative bound state. Right? So let's solve this for E. Now notice that once we know what this E is, then we can solve for g of k from this equation here, right? Because again, we know the right-hand side, and we will have the full solution. And in fact, in the last homework, you will look into that in some detail. Okay, so how do we solve equations like these? Well, if you substitute that free energy in here, this is just some simple three-dimensional sum, which we can turn into an integral in the usual way. And let's just do that quickly, because again, this is something that we did before a number of times. So we can turn it into an integral over energies from EF to EF plus h bar omega c. We're integrating the epsilon. We used appropriate density of states to convert the momentum integral into the energy integral. And then we have this. And now we will make an assumption, as usual, that the density of states of our free electrons does not vary significantly in this narrow band between the Fermi energy and the cutoff, so that we can approximate it by the Fermi energy at the Fermi surface. And then the rest is an integral that we can actually do explicitly. And this integral is just a log. So let's calculate the log. So this is 1/2 n EF times the log of 1 plus 2h bar omega c divided by 2 EF minus E. Okay, and let me just put 1 over v here, which is the left-hand side. So we want to, again, solve this equation for this unknown E. And the way we do that is the following. We divide by NEF and multiply by 2, then take an exponential of both sides so that we get rid of this log. And what we end up with is an equation like this: 1 plus 2h bar omega c divided by 2EF minus E is E to 2 over V times n of EF. And at this point, in order to solve for E, typically what people do, people make a weak coupling assumption. Namely that V times n of E is much smaller than 1, which tells me just that the potential here, V, is much smaller than something. So I'm interested in this problem in the limit when my potential is very small. In that case, of course, what happens is that this denominator is very small, so the argument of the exponential is very large, which means that the left-hand side must be large, and 1 is not large, so I forget about this 1, and I can then solve this equation because I just invert things. And what I find is I really ran out of space today. Interesting. So let me finish it here. So in these approximations, I find that the energy of the bound state is 2EF minus 2h bar omega c times e to minus 2 over v times n of EF. And this is an important result because it says that it's a bound state. It has energy lower than 2EF, which would be the minimum energy that you can add 2 electrons to a Fermi sphere, right? This thing here is positive, so it has energy 2EF minus some positive number. So it's bound state because E is necessarily less than 2EF. And also, it's a non-perturbative result. In V, right? It has V here in the denominator of the exponential. So if you try to expand this in Taylor series in V, you find that it's an essential singularity. You cannot. So there's no hope of actually getting this result in any finite order perturbation theory. And that also explains why many approaches before BCS failed, because they try to, carry out some perturbative calculations to high order, and this tells you that that's always doomed to failure. Superconductivity is a non-perturbative phenomenon. Any questions? So I will stop here and talk more about the Cooper instability tomorrow, and then we discuss the Schrieffer BCS wave function and its properties and consequences on Friday. Okay, thank you very much. See you tomorrow.